All right, so it seems like it's 4 minutes past, so I think it's a good time that we start with our webinar. So welcome everyone. My name is Ivan Lazar Bundalo. I'm R&D engineer at CSEM, and today it's my pleasure to be your host. On yet another cFLOW webinar. So like every time I will start with a bit of explanation of what cFLOW is. Then I will introduce our speaker and then hand over the floor to our speaker. So cFLOW stands, as you can see here, for Coherent Ultra-Fast Long-Wave Infrared Communications. cFLOW is a Horizon 2020 project, so it's funded by European Union international project, aiming at developing the part of the spectrum that so far has not been developed. And to look into that, so this long-wave infrared wavelength region, it makes sense to look at the atmosphere and the absorption of different wavelengths in our atmosphere. So on this graph, on the left-hand side, I'm just gonna take the laser pointer. So on the left-hand side, you can see the standard radio, television, and mobile network. So the infrastructure that has been developed since the 60s, maybe even earlier, for the non-directional communication. Then on the other side of the spectrum, we have the visible spectrum, and we have a spectrum around 1.5 microns, which was developed around fiber optic technologies. So this is what is the backbone of the modern telecommunication systems. If you go a bit further higher to the spectrum of 8 to 14 microns, we are entering the domain of long wave infrared region. That's the region which, as you can see over here, also has a dip in the atmosphere, in the absorbance, which means that the light can go much further through the atmosphere. And as we've shown in some of the previous webinars, the effects of the atmosphere are much lower. So cFLOW is the project which is aiming to develop this wavelength region and all of the corresponding technologies. So the goals of the projects are really to develop this 8 to 14 micrometer spectrum, part of the spectrum, for the free space communications, which so far were untapped, and to develop them for the unmatched speeds of 20 to 100 gigabits per second. These systems would be operating at the room temperature, and they would be very compact. So they would be using the photonic integrated circuits technologies. So now it is my pleasure to introduce you, Doctor. So I actually made a bit of a mistake here. It's Mr. Rony Joss James, who is also my colleague, who's going to talk today about the packaging of miniature optical components. Rony, are you with us?
Yes, Lazar. So
very good. So I would like to read first a bit of a short bio to present you. So Rony is a project manager at CSEM in Switzerland. He's working at CSEM since 2007, focusing on integration of microsystems. He received his master's degree in micro and nanotechnology from Helsinki University of Technology in 2006. And he has more than 16 years of experience in development of microsystem packaging technologies, focusing on topics like hermetic sealings and feed-through technologies for micro-implantable devices, fine pitch bonding technologies, reliability analysis, photonic packaging, and hybrid integration. He is currently the chairman of the IEEE Electronic Packaging Society Swiss chapter. So welcome, Rony, and very happy to have you with us.
Thank you, Lazar, and thanks for calling me a doctor. I always wanted to do it, but couldn't make it yet. But,
well, your knowledge is definitely up there, so
yeah,
no shame over there.
Yeah, but thank you very much for.
Some of us could be ashamed of our knowledge in comparison to your know-how.
Okay, thank you very much, Lazar, and for the kind introduction. So maybe I can start sharing my screen now.
Yeah, that sounds good.
Yeah.
That's good. We can see it. Maybe if you could put it in a full screen mode.
Okay, you can hear me well and see it well, right?
Loud and clear.
Okay, very good. So Good morning, everyone. So some of you I have already seen and met, some of you not. So I hope you are all doing well, and thank you for attending this webinar, where I will be speaking about challenges in photonics packaging. But I will emphasize a little bit on things or topics that we are focusing in the cFLOW project. So before we go, it's a tradition to speak a little bit about our company. So what is CSCM? If you don't know yet, or if you have not come across CSCM yet, we are a research and innovation center in Switzerland. And as you can see here, I'll just start my laser pointer. So we are at 5 different locations in Switzerland, and I and Lazar and almost all the people who are working from CSCM in the cFLOW project are located in Alpnach, which is in the central Switzerland region. So what does CSCM do? It's basically what we, as I said, it's an innovation center. We are developing microtechnologies, not only in photonics, but also in many other different fields, and transferring this to the industry. So, so the main idea of CSCM is to support the industry in Switzerland, not only, but mainly. And also, we are also making new ventures like spin-offs. And as you can see in the past 20 years, we have made around 44 new ventures in Switzerland. Right now, CSCM is a non-profit organization, but a private company, which is a bit strange. People ask me, so what is the idea behind why would the shareholders invest in a company which is non-profit? So CSCM is founded by a lot of industries in Switzerland to move the research or to continue the research inside Switzerland in the microtechnology sector. And CSCM have grown to around 550 people now. So from when I joined, it was maybe 350 people. So it's a big change. One part of our technologies that we are developing is also photonics. This is one of our main research fields. So today, as I said, I will be speaking about photonic packaging, that's what we are doing in the cFLOW project. So what differences do you see here? So on the left side, you can see electronic systems, and on the right side, you have photonic systems. I should say, I mean, electronic systems is also quite challenging, and you can see we call it state of art, but you see there are so many small things which took a very long time for development, like the wire bonds here. You know, if you think about it, everybody takes it for granted, but actually it's a real great development how we can do such thin wires and bond to such small pads. But actually, we have come across the electronic systems a lot, and we have learned a lot of lessons, and a lot of things has been standardized. But if you see the photonic systems, you see a big difference. There are less standardization. So I would give you maybe 10 seconds to think about what are the differences you see here and here on the electronic systems and the photonic systems. I promise you, I won't go for a coffee. I'll be still be here. So 10 seconds. Okay. So what do I see actually? I know you cannot speak because Lazar has muted all of you. So what do I see actually is there are a lot of multiple miniature components, and they are very densely packaged in the optical packaging systems or photonic packages compared to the electronic systems, obviously. So, and you see they are densely populated, but one are related to the other very well. You know, you can see they're aligned quite well to each other. And what you also see is a lot of metals No PCBs, you see mainly gold and copper and everything, which is basically the thermal management. So there's a lot of heat. Not all the lasers are not really highly efficient. So you need to transfer a lot of heat. Not only that, you also have to have the lasers or other optical components at a specific temperature to have it operational with the right specifications that it needs. And other than that, we also have other issues that you don't see, obviously, is the long-term stability. If you have an aligned system, because you don't want to lose the stability for years to come. That's why it's also important to seal it hermetically and to have everything really stable for a very long time. And obviously, compared to the electronic system, you also need an optical transparency here. And maybe you have come across, or what Lazar showed you right now is also that we need very high frequencies. Otherwise, it doesn't give an advantage to other systems. Because the biggest advantage that we also say in cFLOW is the bandwidth that we can reach is very high. So this is also important to have a very high frequency compatibility. So right now, I will focus more on this multiple miniature components and high precision alignment, because that's the focus that we are, that's what we are focusing in cFLOW project. Obviously, the other things are also important, like the thermal management. We are also focusing, but right now we have less focus on it. And also the other, the high frequency is also very important. But I will speak more about the multiple miniature components and the high precision alignment. And in the project, I think we are not going to work on hermetic sealing and long-term stability. So active alignment, so high precision alignment. There are two different types of alignment, as you might know already. That's one is the active alignment, where you have, for example, that you see is a fiber which is coupled into a PIC. And how you do it is, in active alignment, you align the fiber to the PIC by seeing the output of the PIC to see how much power or intensity is coupled into it. And so you have a feedback loop. So you check how much intensity you have, and you change the fiber accordingly. And then you wait until you, or you move it until you have the best configuration. But in a passive alignment, you don't have a control loop. Basically, what you see here is a, sorry, that was a mistake. This is a VCSEL array here, and this is a lens array. So if you have very accurate structures which you can align to each other, then you can just bring them together with the machine in a passive way. So what you do is look at different structures on the chip and the lens array, and then you have a very good alignment. Okay, very good. What is the difference then is that you don't have a control loop, so you don't see the output. You're just focusing on the structures on both the chip and the substrate. So what is the difference between these two? Basically, as you might have already guessed, passive alignment is quite fast compared to the active alignment. So in principle, that also says that the cost of the passive alignment is much lower compared to active alignment. So the alignment of passive alignment usually takes much lesser time, can be less than 1 second in some cases, depending on the accuracy required. And also in active alignment, you have tens of seconds to maybe minutes, depending on the complexity of the parts. So what we have, or the industry standard of achieving, is passive alignment has come maybe near to 2 micron accuracy tolerance. but with a little bit of more time. So it's not so fast as 1 second, but it needs more time. So I give you a couple of examples of passive alignment and active alignment. So this is, for example, transceiver application that's what you see here. So what we have to do is to have VCSELs and then using optics to couple it into a fiber which is outside of this package. So as you can see, this is a good example where we can use passive alignment. As you see here, this is the simulation of seeing ray tracing simulation to see how much. This is the sensitivity analysis to see how much tolerance you have. As you can see, it's plus or minus 10 micrometers is the tolerance required here. This can be easily achieved with the die bonding or flip chip machine. So this kind of application this is an ideal case for a passive alignment. And this is, for example, here you are focusing the beam, and here you have collimating the beam outside. So in this case of collimation, you can even have a larger tolerance. So this is much lenient compared to this case. So what was the criteria here? We were looking at a tolerance criteria was a coupling of 90% or more into the fiber, which is outside of this package. So what we achieved, this is, for example, the samples we have already manufactured. This is a ESA funded project, and we could achieve quite well the 10 micron alignment tolerance that was needed for this packages. And as you said, it's passive aligned, so it's a much faster process in this case. So in case of active alignment, why do we need active alignment then? So there are cases where you need much higher accurate alignments. For example, in the case here, you have a fiber and you want to couple from a PIC, which has a very small size compared to a fiber. You have obviously the fiber is already only 9 microns, and your tolerances are maybe 1 to 3 micron tolerances. And for example, PIC, from when you couple this to this fiber, this is quite difficult because you have a large difference in the modes. So you have to use an edge coupler. And as you see, you increase the size of the mode field to a bigger size of around 3 micrometers here. And then you have alignment tolerance of less than 1 micron, which is very difficult to achieve in a passive alignment form. So this is an example where it would be very important to have an active alignment compared to passive alignment. So this is an example of such a system which was fabricated here. Here we have a fiber which is coupled into a photonic integrated circuit and going out into another fiber. So here we need a very precise alignment, and this was done with active alignment with sub-micron accuracy. So this is just magnification of the PIC and how the fiber is coupled into the PIC. So I have a video of how this alignment is done. So as I told, the passive alignment is improving and active alignment is improving. So active alignment is improving in the sense that things are getting automized. So a lot of processes can be made much faster. So I have to start the video now. So what you see is first the calibration of all the stages. It has a 6 degree of freedom. And now this is a fiber feeder, which is coming into the package. And then this, we are inserting the fiber here, which is right now manual, but it can be easily automated. And And now the active alignment phase, where you come with a photo detector on the other side of the to see how much laser or light is coupled. And so you can align with actively and depending on the output on the photo detector. So that's one of the examples where we need active alignment. So this is basically what you see on the photo detector. That is how you manipulate the fiber and to see get the best output out of it. So what is happening now is, as I said, the passive alignment is trying to improve and active alignment is trying to improve. So passive alignment is going more in the range of 1 micrometer, and active alignment is going also in the other direction, where it tries to be faster by making automated processes. But there are still some advantages of each of the methods. For passive alignment, we can use many different bonding methods after aligning, like soldering or silver sintering or adhesive bonding, which is not the case in active alignment. You're restricted to adhesives because you cannot heat up the part during active alignment, or it's very difficult, and you have less freedom to move when you have a solder or a silver sinter. And right now, the passive alignment has the equipment are quite standard or state of art, so they are less expensive in many cases, depending on the accuracy. And in the case of active alignment, there can be more expensive. Obviously, we have still less accuracy here in passive alignment compared to active alignment. And the benches, you need very highly accurate structures on the substrates to have the alignment properly. So this is also very important. So as I said, with active alignment here, what is the improvement is what we are trying to do or improve is to have automated, the processes should be more automated. The most time consuming part here is to scan so first you have the first light detection, where to find where the light is when you couple in, and then to find the optimum, it takes a very long time actually. So there's a lot of steps involved in this. As you can see, you have to scan the whole area, and once you find the spot, then you have to scan it fine to have the best output. So this is where there's a lot of time needed for this step. So what we are working on is machine learning and other smart algorithms to improve the speed at which the active alignment can be done. On the other hand, for passive alignment, the more work is being done on machine accuracy and speed improvement to have a very fast process, and obviously improving the alignment accuracy with very accurate structures. Like now a lot of people are also trying U grooves instead of V grooves, so that it fits the fiber much better, or very highly accurate lithographic structures. So this manufacturing of the structures are getting more and more precise. And also there is more development to make it even more low cost, using low cost optical benches, sometimes also with molded plastics. But as you know, it has less precision, so it's less accurate, but it has a very high cost advantage. So you could use it for some systems where you don't have a very high accuracy requirement. So now that was just an idea of what is happening around this field. Now in cFLOW, the objective is to align 3 different parts together, 3 different components together. One is a QCL laser, as you see here. Then there's a modulator, then there's an amplifier after that. What is important is they are all aligned well, and the light is going from one to the other in a very aligned and without a lot of losses. So that's very important. So what we are trying here is a passive alignment due to many different challenges that I will explain in the next slide. And what we are depending on is using very highly accurate lithographic structures so that we can align it quite precisely. So what we are doing is a butt coupling approach. So this is a QCL, a modulator, and the amplifier. So we have, as it's an edge emitter, we are going to align the modulator very well to the QCL and amplifier to the modulator in a butt coupling fashion. So this will be die attached onto a substrate, and everything has to be quite stable, and it has to be very well aligned. So we are using passive alignment. Why are we using passive alignment? The reason is, first thing is thermal management. So we have a lot of active or 3 active components here, and so using of adhesive is not really advisable. So we have to use higher thermal conductivity materials as the die attached material. So this is a case this is a case for solders or silver sinters or metal based joints, and this cannot be achieved with active alignment. And the second thing is the high frequency compatibility. So we cannot use adhesive also because we want to do a flip chip so that there is no wire bonds needed on all these devices. So if you have wire bonds, you are restricting the frequency achievable. So as you have seen in the other presentations, we are trying to achieve very high frequencies above 20 gigahertz, much above. So it's very important that we do flip chip interconnections here. Active alignment is very complex as all the parts are very active components, no passive components like in the case of a fiber. And miniaturization is also critical. So you cannot use lenses in between and to steer the optics so that you have a better alignment. So what are the challenges here? So this is sensitivity analysis to check what is the alignment tolerances possible in this configuration. Here you have the QCL and the modulator, and you see this is a gap between them. This is what is simulated here. As you can see, this is the distance between the QCL and the modulator. So as you see, this has a biggest impact compared to this, which is the X direction offset or the Y direction. Y direction is in this direction, moving up and down, and the X is perpendicular to this direction. And as you can see, it's very important to have the modulator very near, as with a 5 micron gap between the QCL and the modulator, you have a loss of around 45%. And when you have aligned on the top of that, you have other losses. So it's really critical that you have a very dense or very less space between the QCL and the modulator. And this, as I said, is the X direction, and this is the Y direction, which is also quite important. But as you can see, you could have not in a lot of micron range, but maybe 2 micron difference is also not so bad. You still have a quite good coupling efficiency here, even if you have 2 micron difference. So with this, it is already quite challenging for a passive alignment. As you can see, everything adds up. So you have to have a better than 2 micron alignment accuracy in the X and Y direction, and in the Z direction, which is the distance between the QCL and the modulator, you have to go as near as possible, which is quite challenging because you might have some discrepancy at the borders of these materials, and it's difficult to get it nearby. So this is, we also analyze the tilt, what happens if there is a tilt around. As you can see, it was not a big constraint here. The assumption is always that we are keeping the distance between the chip of 5 micron, then you have quite a good coupling efficiency if you have a tilt of even 4.5 degree. So what are the different challenges here? So it has to be very highly accurate placement. As I said, it has to be better than 2 microns, at least. Always the better. If you can get much better, you have more coupling efficiency. Then we are using very thin gold tin solder, which is less than 4 micron here as a die attach material, so that we can reduce the Z alignment, or as we call the height alignment tolerance. And we have to also use a fluxless solder because we don't want to contaminate the facets, which is because it's very near to the solder interface. And the design of parts to enable integration is very important. We have to really control all the sizes here of the chip and compared to each other, and also the solder, so that we have the best outcome here. And it's also important to have the right material. So with a small change in the CTE, you already lose a lot of alignment. So it's a sequential process. That's another challenge that we have here, which means you have to bond one after the other, so without affecting the previous assembly. So you don't want, when you if you're bonding the QCL first and you're bonding the modulator second, you don't want the alignment to be lost for the QCL bond. So this is very important that it stays there when we do all the processes for all the steps. So what we are trying to do is to use few different approaches of step soldering, which means basically that you don't remelt the part which was already bonded when we do the other the other parts or bond the other parts. So the first method that we are trying to use is a transient liquid phase bonding, where we do change in phase of the solder so that it doesn't remelt anymore at the melting point of the solder. So once we make a bond, for example, we make the bond of the QCL on the aluminum nitride substrate, we change the phase into a gold 5 tin or CETA phase, which wouldn't remelt below 400 degrees. So which makes it possible for doing the other assemblies without disturbing the first bonds. This is one option that we are doing. Here are some cross sections that you see. This is as deposited. Then you form the eutectic solder, which is the melting solder. And finally, you have the TLP phase, which is the gold 5 tin phase, which is completely, the solder joint is completely changed into this phase, and now it won't remelt after that. And we are also working on a hot chip method, wherein we are trying to only heat the chip with the chuck at a temperature lower than the melting point of the solder. By this, we don't melt the solder which is nearby the chip. For example, when we do this bonding, it won't disturb the solder under the second chip. So this is one of the other methods we are trying to develop here. We have other methods we are trying, but I'm not going deep into it right now. What I would like to show now is some of the preliminary results that we achieved. So as I said, parallelism and the alignment accuracy is very important here. So what we achieved, as you see here, is a QCL and a modulator bonded one relative to the other. And what we could achieve is a parallelism or a height control of 0.5 micrometers. So this is quite good in terms of what the requirement is for such for this system. And the second thing is we have a placement proximity, which was very important, as I mentioned in the previous slides, which is the distance between the QCL and the modulator. And as you can see, we could achieve a very good placement accuracy or proximity, and this is also less than 3 microns. So I think we would be able to achieve better than the specifications at this point. But I should say we haven't done any real tests with real devices. These are dummy devices, so we will have to wait and see what happens, or we really have to test the output of the laser power to be sure that everything is working properly. But this is a very good start, and we hope to go forward, and maybe in another webinar we will have more results on this. So what are the other challenges? So as I was focusing on the alignment, but as I said, there are a lot of other challenges for photonic systems. What is very important is thermal management, so that all the heat generated by the devices are somehow managed and taken away. This is very important, and so we also have to control the temperature to less than 1 Kelvin, or even better than 0.5 Kelvin. So this is also a very big challenge, and it has to also have a very high frequency compatibility. So what we were focusing on is this right now, but in principle, this system will really look like that, where you have a lot of thermal management materials here, like you have a heat sink and a tech, and again a heat sink or a cooler to reduce the temperature and to control the temperature. On the QCL, we will have to use a control loop with the NTC on it. And also the high frequency is also important. So what we are trying to do is also to have everything integrated, also to have the high frequency connectors which can be directly implemented or contacted on the substrate here, where we have aligned the parts together. So conclusion is, packaging has multiple challenges. So what we have to be very careful is the design for integration. So the integration has to be thought about already before or designing the parts or components. And it's also important to think about the probabilistic design for reliability, which means you also have to think about reliability, what kind of materials to use. And alignment is still challenging, but evolving in to make things faster in case of active alignment, and more accurate in case of passive alignment. And passive alignment used for reflow, as you can see, preliminary tests shows very good results that the required accuracy can be achieved. But more challenges remain. So I think maybe we'll have another webinar to talk more about the results we achieve here. Thank you very much for your attention, and I'm open for questions.
Thank you, Rony, for a very interesting webinar. We have already more than a few questions, so let's dive into them straight away. So there's one question: is there shrinkage associated with liquid phase bonding?
During liquid phase bonding, there's very less shrinkage or almost no shrinkage. The only thing which can happen is during the cooling down phase, there's obviously a shrinkage because of the CTE of the material itself. But it's very small compared to an adhesive, because you have a solder, for example, has a CTE of depending on the solder, obviously 10 ppm per degree Celsius, which means it's very even if there's a shrinkage, it's very less. And the good thing is everything goes in the same direction, which means if there's a misalignment, it all goes in the same direction.
There's another question which is kind of related to that. So it's related to several different chips that are being put on aluminum nitride. There's actually two questions on that. The first one is, how much can you adjust the height of a second and third chip to the first one? Do the capillary forces play a role when placing those chips down?
What we do is here is, as I said, the XY alignment is done with very accurate structures. This is giving the really high accuracy here, but Z control is very important as you are asking here. So it's a challenge. What we are doing is we have two different options that we are trying to implement in this process, which is Z control. The machine itself that we are using can have a specified height that where you bond. So you can go to a specified height and do the bonding there. The second option is to control with pressure, because the cold tin is a hard solder. When you bond, you need to apply a pressure, and by controlling the pressure you can adjust the height quite well actually. And so it's challenging, the height control compared to XY control, but I think right now, as we see from the preliminary results, we have good results, which is around 0.5 micrometer thickness accuracy. And as we use a very thin solder, which is also helping, because you cannot go 10 microns because the solder is already only 4 microns.
Thank you. So the other three questions, they're all related to that somehow. We have a question here. So on one hand, we want to, when you're stacking these several components together in the project, we want to put the components as close as possible, but on the other hand, we want to also have them thermally independent, which could be achieved by putting them further away. So how can we manage optical needs with thermal needs? So since laser and SOA are typically heating during the operation, do you find that there is a critical point or in the butt jointing integration seen with aluminum nitride substrate that's not such a big issue?
I think it would be very difficult to control the heat, to have a different heat on each of the parts, because what we try, at least in the design here, is that we are using the best thermally conductive materials, like which can be usable. Obviously, there are better ones like aluminum nitride. So you'll have a thermal heat conduction or spreading quite fast. But obviously, what we have to think about is the heat spreading is also depending. The direction of the heat spreading is also important, which means the heat flow goes more down than to the sides laterally. And we are trying to control the temperature, as I showed you with the tech and Peltier. So we try to have a temperature for all the parts at the same temperature, which means there is no change in temperature. This is what we are trying to achieve here. But main issue is for the QCL. Maybe our partners maybe have another opinion. Maybe we can discuss this, but we haven't thought about temperature as an issue for the modulator. But it's an important question that we have to look into it if this is an issue. Yes, but right now we don't have an idea, or we are not having a strategies to have different temperatures at different chips.
Thank you. So now following on that, when you're doing the SOA and the QCL and you're stacking the components one beside the other, how do you make sure that there is no short circuit when you're bonding parts so close to each other?
Yeah, so that's also very challenging, as you see, when you bond things as close as possible, 1 micron, 2 micron, 3 micron to each other, and the solder is everywhere, then it's quite challenging. So what we are trying to do is obviously to have a very good control of the solder width and length, and to have enough space for the solder to flow so that it just reaches the edge of the chip. It's quite a challenging task, but with the right process and pressure, you should be able to achieve it. What is important is for the QCL, you should have a very good contact, thermal contact. So it should be flowing everywhere and it should be completely bonded in all the areas. So you cannot leave a small area on the side to avoid this short circuit. Maybe in the case of the other devices, it's a bit less critical. So you might play with solder of slightly smaller size compared to the device itself.
Thank you. And then maybe the last question, what would be the maximum alignment accuracy that you can achieve with passive alignment at CSEM?
Yeah, I think so. The machine itself is better than a micron accuracy, so sub-micron accurate bonding machines. So obviously there are some tolerances on the structures and the alignment structures, and there are other tolerances coming into play. So I think less than around 1 micron should be achievable in a passive alignment with our in this case of where you have very stiff parts like aluminum nitride and very well controlled alignment structures. It should be able to achieve around 1 micron accuracy.
Very good. Thank you, Rony. It seems like that these were all the questions that we had for now. This was really interesting, and thank you for the insight into the work and problematics and the technologies which are being used for tackling these problems. So what I would like to do now, if you wouldn't mind, I'm going to share my screen.
Okay, thank you very much again, Lazar, and everybody for joining.
Thank you. So I hope you can see my screen. So I just wanted to say that these videos and recordings are going to be on our cFLOW webpage. Here you can also find a lot of other information about the project, about the technology, about the partners. So please do visit the webpage and reach out in case that there are questions or interests. And I would also like to announce the following webinar. So the fourth iteration of our webinar is going to take place in 2 weeks' time, so May 25th, again at the same time, 11 a.m. CET, same link again, where we're going to have representatives from Mirsense and Technical University of Vienna, so Gregory Maison and Borislav Hinkov, talking about quantum cascade lasers and amplifiers and mid-infrared plasmonic waveguides. So make sure you tune in then. If not, that video is also going to be available online soon after the webinar. And with that, I would like to close the webinar and thank you again, Rony, very much for your participation and for the presentation. And thank you all of you participants for following. I wish you a great rest of the day.
Thank you. Bye-bye. Bye, sir.
Thank you. Bye.